Hi everyone, I'm Changyu. I'm a PhD student in Mobile Robotics and Intelligence Lab in KAIST. The topic of my presentation is nonlinear model predictive control for autonomous navigation in a canal environment. Recently, interest in autonomous surface vehicle is increasing along with robot technologies. For more advanced autonomy of surface vehicles, it is necessary to consider more complex and challenging marine environments such as canals. In this environment, more sophisticated local trajectory planning and tracking algorithms that can detect and avoid the surrounding objects are essential. In this study, an NMPC-based control algorithm was proposed for safe autonomous navigation in a canal environment. And it was experimentally verified using a 12-person cruise boat in the Pohang Canal in South Korea. The Pohang Canal is a canal located in Korea with a narrow and complex geometry of about 2 km long and an average width of 15 meters. It is a challenging environment with the structures of various shapes around it. The contributions of this study can be summarized as follows. Uh, Various structures existing in the canal were clustered into line segments of finite length, and they were set as a constraint of the NMPC algorithm to guarantee the safety. The algorithm was implemented in real time, and the ship's motion characteristics and input saturation were also considered in the proposed algorithm. And the performance of the proposed algorithm was verified in an real-world canal in the Pohang using an 8-meter long cruise boat. This is the target boat. The length is 7.9 meter, and there is GPS and AHRS and 3 lidars in starboard side, port side, and front side. MPC is a model-based control method, so it is essential to understand the mathematical model of the target ship. The relationship between steering angle and steering command, and the relationship between thrust command and RPM of the propeller were identified using the obtained data. And this data show that our relationship is linear, like this graph. Using the obtained control coefficient, and the rest of this system was identified through the following method. The cost function minimized the error between the actual acquired data and the simulated data through a model composed of unknown parameters. Here the unknown parameters are the mass and the linear and quadratic damping matrices, and this is the dynamic model is composed as the below equations. To identify the system, we gathered data in an open water area. We conducted acceleration and deceleration and zigzag maneuvering experiments, and we obtained lots of data, and with this data we estimate the unknown parameter with the optimization problem established in the previous slide. And the light graphs are results of the parameter estimation, and here the green line is the estimated result. And as you can see in this slide, the identified model is quite reliable. And detect obstacles in a waterway and consider it in an NPC framework. We process the point cloud obtained from 3 different lidars and parameterize it as combination of line segments. To process it, we thresholded the point clouds and used Hop transform to extract the line segment from the thresholded point clouds. With identified model and detected obstacles, we designed an NPC algorithm like these equations. There are 2 cost functions. First one is L and second one is LT. L indicates the stage cost, which penalize the stage error and the efforts of control input. And LT represent the terminal cost function, which penalize the terminal stage error, like these equations. And there are also lots of constraints. First one is initial state, and second one is dynamic model, which is identified from the previous slide. And there is also input saturation, and last one is obstacle avoidance constraints. The obstacle avoidance constraints are represented like the last equation in this slide. This equation is represent the the meaning of this equation is the ship do not collide with the line segments like the right above figures. So with the nonlinear dynamics and obstacle avoidance constraints and reference paths and this objective function, we uh, we can design the NMPC algorithm like this, and we use this algorithm in 10 Hz in real time, and we calculate the control input, and we use this control input to the vehicle like this this block diagram, and we used EKF to estimate the state during the experiment. This is the result video, and this red and orange point clouds are the LiDAR point cloud from 3 different LiDARs, and these blue lines is reference paths, and the detected obstacles are represented here as a white wall like this, and the resulting trajectory is represented here as a green line like this. And we also shows the synced GoPro video and Google Map video like right videos. This is the result of my research. And we also compare it with a baseline approach. Uh, this is the baseline approach. This uses 2 separate algorithm modules. The first module is path planner, which is same as model predictive control, which I designed here, but they use this algorithm for only generating a collision-free path. And they use ROS guidance and PID controller to track the generated path like this. But in my study, we use only an MPC module which can generate the collision-free path and also can calculate the optimal control input simultaneously. So we compare the the safety constraint, how proposed methods guarantee the safety distance during the experiment, and we also compare the control effort like this table. As shown in this result, our proposed method can guarantee the safety distance more well than the baseline algorithm with the less effort of control input. To wrap up my presentation, we proposed an MPC-based optimal trajectory planning and tracking control algorithm for a cruise boat in a Canal environment. To design an MPC algorithm, we identified the system model with experimental data, and we parameterized the surrounding obstacle structures in the form of line segments. And with this algorithm, we conduct experiment in the Poan Canal and compare it with the baseline algorithm, and we can verify that our proposed algorithm shows better result than the baseline algorithm. And this is end of my presentation, and thank you for your listening.